So let's start off with some questions just using the basic voltage equations. So we've got a charge that's moved from point A where the potential is 300 volts. So we've got point A and we've got VA is 300 volts to point B where the potential is 150 volts. So here's point B. VB is 150 volts. And the charge goes from A to B. So I've got some charge. I don't know whether it's positive or negative. It's moving from A to B. And we know the electric field is going from the big voltage to the little voltage. All right, so what do we know? Well, we know our potential difference is V final minus V initial. So it's 150 minus 300. So I get minus 150 volts. And it's important that you do it in this order so you get the sign correct. Okay, so what I know is that delta V is minus 150 volts. And from the problem also, I'm told that it's 4.5 times 10 to the minus 4 joules is my change in potential energy. So my change in potential energy, if you remember the equation, is Q times delta V. So I know my delta PE, I know my delta V, and so I just have to rearrange it to get my Q. So Q is equal to delta PE over delta V. So that's 4.5 times 10 to the minus 4 over minus 150. And I get minus 3 times 10 to the negative 7 is my charge. So the units for that is coulombs, or minus 30 microcoulombs. So that tells me that it was a negative charge that I moved. If my voltage sign were opposite, so if I'd moved from 150 to 300 and had the same energy change, then I would have got a positive charge. Okay, let's do another one that's very similar. A proton with an initial speed of 800,000 meters per second is stopped by an electric field. What potential difference was applied? Okay, so what we know is that we have a proton, so we've got a positive charge of 1.6 times 10 to the minus 19 coulombs that's moving along with V initial of 800,000 meters per second. And we apply an electric field. So remember, the force on a positive charge is in the direction of the electric field. So if I want to stop it, I want to apply a force in the opposite direction. So I'm going to apply an electric field like this. So my force is equal to Q times E. Okay, and that's going to slow it down. And so my final speed is going to be 0. All right, so what do I know? I know that the work done by the electric field, the work done is Q times E, force, times distance. Okay, so that's the work done. And that's going all the way back to physics 1, equal to the change in kinetic energy. So change in kinetic energy is 1/2 m times V final squared minus V initial squared. So if I plug in my numbers, the mass of a proton, I can look that up in the back of the textbook or just ask Mr. Google. 1.67 times 10 to the minus 27 kilograms. I've got 0 for V final, 800,000 for V initial, and if I do that I get negative 5.344 times 10 to the minus 16 joules. Okay, so it's quite a small energy change, but it's also quite a small charge. All right, so how do I calculate the potential difference? All right, well, what I know is that potential difference, delta V, is the change in potential energy over the charge. Okay, and I know what the charge is. Or that's equal to minus the work over the charge. Okay, so I've got my work, which is delta KE. So my work is minus, I'm going to have two negatives here, so let me do this. The negative of minus 5.344 times 10 to the minus 16. So two negatives gives me a positive over the charge, 1.6 times 10 to the minus 19 coulombs. And I get 3,340 volts. Okay, so with these two problems, we just played around with the definitions of voltage and work and potential energy.